classwork 4.8. So the beginning here is just to make sure you're clear on the fact that there are three words that essentially mean the same thing. Root of a polynomial means the same thing as a zero of a polynomial, which means the same thing as the x-intercept of a polynomial. Usually the x-intercept is brought in when we're talking about the graphical nature of a root or a zero, but these two words get interchanged constantly. And I'm going to interchange them to make sure that you keep in mind that they mean exactly the same thing. Now, the fundamental theorem of algebra, very important theorem, says that a polynomial of degree n has n complex roots. But what is meant by a complex root? So the roots you've seen so far, the zeros, have been real numbers. And when you find a real number 0, x minus that real number is a factor of the polynomial. And I've given you problems where you have the factored form of a polynomial and you graph, so you know to solve for the equation equaling 0 will give you an x-intercept. So if you know the x-intercept, x minus that number is a factor. And just depending on how many factors there are, I have the dot, dot, dot in the middle. Then this is your leading coefficient. If you are not given enough information to have a known leading coefficient, just make it 1 to make your life easier. Now, what is a complex number? You are used to dealing with just real numbers. You started off with a horizontal number line with 0, 1, 2, negative numbers, and you dealt with all sorts of real numbers, fractional numbers, and everything on this number line. That number line represents only real numbers. Every single point that makes up this line is one of your real numbers. Now, if I want to look at an imaginary number, I have to go from just a single dimensional line to a two-dimensional plane just to talk about one complex number. Now, on this complex plane, 1 represents the imaginary number I, 2 is actually 2I, and then negative going down the way. And so if I told you to write the number 3 plus 2I, if you were to plot that in the complex plane, that would be located right here where 3 and 2I come together. So what you want to realize is complex numbers are far more than just the real number system. And when we go to graph a polynomial, we have a one-dimensional input coming in. If we had to go complex numbers, we would need to look at a two-dimensional input coming in, as well as a possibility for a two-dimensional output. So you almost have to imagine taking this plane and think of it as being vertical, and then turn it to make it flat. And then from there, you can create a four-dimensional polynomial because the output answers are also two-dimensional. So it's going to be really hard for us to see 4 dimensions, so we don't go into the graphing nature of the imaginary number. All you need to know at this point is that the imaginary number is representing the square root of -1. we are not able to, within what makes sense to us, come up with a number who is equal to the square root of a negative number. Now, it's unfortunate that it was named an imaginary number, but that's just the name. It is something that exists, but it's not easy to see or contemplate. Know that when you write a complex number, the A and the B there are representing actual real numbers, and you have your real part and your imaginary part. Now that you don't necessarily need for what's coming up. And realize that every time we deal with a real number, we actually are working with a plus bi, where b is equal to 0. Now, the first example we are going to take a look at is not going to involve the imaginary numbers, the complex numbers yet. We're going to look at creating a polynomial with the real roots. If you have the real root 3, one of the factors is x minus that 3. If a root is negative 4, then one of the factors is x minus that negative 4. If 0 is one of the factors, then x minus 0 is another one of the factors. Now I want to point out that we don't normally write x minus 0. We normally just write x. So when you write this out, usually you put the x in front of the whole thing. And so we are now trying to come up with a polynomial equation of least degree in standard form. Standard form means you have to have your terms separated. You need to know your leading term and all the ones down after that. So you got to multiply it out. Now, the only information I have are 3 roots. So I'm just going to leave it there and not add any more to it. I need to multiply x minus 3 times x plus 4. And I'm just going to take you over to the multiplication to see that. Where did the answers go? There it is. So multiplying just the x minus 3 times x plus 4, the box multiplication gives us x squared plus x plus minus 12 when we combine all of those like terms. Now remember, that is coming from just x minus 3 times x plus 4. We still have x that needs to multiply in. But that you can just distribute through to get x cubed, distribute, 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 to get x cubed plus x squared minus 12x. And that is now the finished problem that we were working on. Then, next, the multiplicity of a root, and this is expressing that the root it's speaking of is r sub whatever k is. The multiplicity of a root is how many times the factor x minus that root is a factor of the polynomial. The multiplicity of that root is counted at within the number of complex roots. So what I'm trying to say here is, let's say your root is 5, and it has multiplicity 2. Then that means you have x minus 5 as a factor, and the multiplicity 2 says it is squared. So this factor x minus 5 is occurring 2 times in this polynomial, and that counts for 2 of the roots guaranteed by the fundamental theorem of algebra. And now we're ready to do another example. This time, you have the roots 5, and 5 has multiplicity 2. So with that, you're getting x minus that root 5. Multiplicity 2 means squared. And x minus negative 1 with a multiplicity of 1, and you don't have to write the 1 exponent. And it didn't tell us any information to come up with a leading coefficient. So the easiest thing to do is just to make that leading coefficient 1, but it looks like I have that down a little bit farther. Now, I would recommend, as you're multiplying, to start with the squared factor. Multiply x minus 5 times x minus 5, because there's a nice pretty pattern to it that makes it easier to work with. We will end up getting x squared minus 10x plus 25. I still need to take that result and multiply it by x plus 1. And so here is the multiplication by x plus 1. And then I add my like terms, so I've got an x cubed with x squared. I add those two together. The x's are added together, and then 25 is alone. There's not enough information to determine the leading coefficient, so the easiest one to use is the number 1. And this would be a correct answer to a polynomial written in standard form with the information that was given. Okay, next, let's make sure that you're aware of the fact that when you square the imaginary number, you are actually undoing the square root. And that is going to leave you with the negative 1 under that root. And the interesting thing is that that's actually a real number. You're going to be using this in just a little bit. Now, if you are dealing with a polynomial with nice real number coefficients, which is only what you're going to deal with, you won't deal with anything beyond that. Know that if you have a root that contains the imaginary number, its complex conjugate has to also be a root. And its complex conjugate creates a pair of numbers where the plus or minus is with the imaginary number. Now let's remember that if you have an actual real number, let's just think of a real number. Let's say 3. If 3 is a real number, then this is a being equal to 3 and b being equal to 0. If b is 0, then the plus or minus sign is not needed, and that is then by itself a root, and any other roots have to be also named separately. But if you had the complex number, let's say 3 plus 5i. In this case, a is equal to 3, b is equal to 5. And if the plus is creating one of the complex roots, then the minus has to come with it. So if 3 plus 5i is a root, then also 3 minus 5i is going to be a root. But that's only if you know that it is a root. And together they count as two complex roots. But a real number doesn't come as a pair of numbers, so it only counts as one of those complex roots. And just to make sure you're clear about what the conjugate pair is, if you know a root is 3i, negative 3i has to also be a root. If you know a root is negative 5i, then positive 5i has to be a root. If you know a root is negative 2 minus 3i, negative 2 plus 3i has to be a root. And so on. 1 plus 6i, also 1 minus 6i. Negative 3 plus 2i, another root has to be negative 3 minus 2i. And then the next example, you have a leading coefficient. You know two roots, but you need to write a polynomial of least degree in standard form. If 2i is one of the roots, its conjugate has to be a root also. So we're going to add on to that list negative 2i, and then that means that you have to have three linear factors. Now we were told that the leading coefficient was negative 3, so I've brought that in front here. And I highly recommend that the first thing you multiply together is your pair of conjugates. They nicely simplify. You want to start there. So here is the multiplication of x minus 2i with x plus 2i. And you want to notice that when you add together these two like terms, you get 0. Here, when you multiply, you're getting negative 4i squared. You want to remember that I squared is equal to negative 1. So what you have is negative 4 times negative 1, and you end up getting 4. So multiplying that pair of conjugate complex numbered factors leaves you with a nice, simple x squared plus 4. So now, going back to the original polynomial, this pair of factors is now x squared minus 4. Still got to multiply. So x squared plus 4 multiplied by x minus 5. And actually, be careful with this and adding your like terms, because I have x squared and then a 4. I'm missing the x term. There's 0x going on. If you want to have those nice diagonal lined up items, then you want to have a middle column where you realize that you are actually multiplying 0x. So you get 0x squared. You get 0 times x. And then you can nicely see the diagonal lineup. You don't have to add that in. Without adding that in, just be careful. If you don't have this placeholder put in, you need to be careful and realize that now your diagonal numbers are not like terms. This actually creates 4 completely different terms. And then the last thing is to distribute the multiplication of that negative 3. And we get this polynomial. And I believe there is one more example. And what you need to understand is when you are told f of some number equals 0, that's giving you zeros x-intercepts. When you are told f of 0, the answer you're getting is the y-intercept. With that y-intercept, we're going to be able to determine the leading coefficient. In the meantime, knowing x-intercepts helps me to know what some of my factors are. But if negative 5i is one of the roots, then its conjugate, positive 5i, must also be a root. So now I have 3 complex roots. I have leading coefficient times x minus one of the roots, x minus another root, and x minus the last root. Now I need to multiply this together. I recommend first multiply the pair of conjugates. When you multiply your conjugates, you end up adding these like terms to get 0. You wind up getting negative 25 times I squared. And again, remember that I squared is negative 1. So altogether, negative 25 times negative 1 gives you a positive 25. And so x squared plus 25 is the multiplication of these pair of conjugates. Now let's bring that back with what we have. And now we need to multiply by x minus 2. Now, it looks like first I decided to find c, which I could do at any time. So if I plug 0 in to every single x, and I would tell you, you don't want to plug in 0 until you get to at least this point, or it might be a little bit confusing as you multiply the complex numbers. However, you might not have a problem with it and you can do it sooner. But when I plug in 0, I end up getting whatever my leading coefficient is, multiplied by negative 2, multiplied by 25 must equal 750. Negative 2 times 25 is negative 50. So then I divide 750 divided by that 50 will be my leading coefficient, and that leading coefficient is 15. And more multiplication is needed. So next I am multiplying x minus 2 by the result I got by multiplying the conjugates of x squared plus 25. Again, you can create a middle column with 0x, and then you have things that line up. If you don't do that, make sure you're very, very careful about adding like terms, because none of these are like. Adding together everything you get from that multiplication, and then multiplying that by the leading coefficient, you end up with this polynomial. And that's it. Now I just have to find the off button.